Today I'm going to tell you a few things about sensors. Now, when I was putting together the presentation, I wasn't quite sure about the level of knowledge you guys have. So if some of this appears a little bit basic, just ignore it. I'm sure there'll be a few things that will help you, and I'm hoping that you all can benefit a little bit from my experience. So as some of you might have noticed, when you start to look into sensors, it really is just kind of a bottomless pit. You can go down this rabbit hole, and there's going to be data sheets for electrical engineers. There's going to be really complex libraries. There's going to be assembly programming and all that. And it can be a little bit intimidating. But all you're trying to do is you're trying to measure something, but then they throw all of this extra information at you, and you really don't need all of that. And I'm hoping to tailor this presentation in such a way that you can have a few basic concepts and give you a few procedures on how to get what you want to do, is essentially just measure something. Luckily, we're kind of in a maker community. We benefit from other people's work quite a bit, and you don't always need to reinvent the wheel. The Arduino has been around for 15 years, the Raspberry Pi coming up on 10, so there is a ton of tutorials, and for any kind of sensor, there is usually something that somebody else has already done. So I strongly encourage that you seek it out and you just try to use those. Sometimes you'll end up spending a few extra bucks, but you end up actually saving yourself a ton of time. So here's kind of how I'm going to structure this presentation. I want to take you from a beginner to a heavyweight. I'm going to go over a few sensor basics, a couple of different sensor types, how to select sensors, and then give you a few steps on how to troubleshoot what you have. All right. So essentially what a sensor does, it takes some kind of a physical concept, be it temperature, pressure, speed, distance, and it turns it into an electrical signal. And then it is, that electrical signal is essentially how you measure things, usually in the form of a voltage. You don't really need to know how exactly it does it. There is chemical, there is mechanical properties for thermocouples, for example, but you don't really need to know any of that stuff. All you need to know is that the sensor somehow gives you a voltage. You can go ahead and look up all of the basics, but you don't always really need to do that. Usually, the way it works is the more of a thing that you're trying to measure, the bigger the voltage difference. Which brings us to these things called analog sensors. So for analog sensors, what they're doing is you have whatever you're trying to measure here, be it pressure, be it temperature, and it's kind of proportional to the voltage. So the more of a thing that you're trying to measure, the bigger the voltage difference. And you can measure that with your Arduino, with your Raspberry Pi. And yeah, pretty much you can just directly do that. One of the drawbacks with these sensors is that, with analog sensors, is that you will need to calibrate. So you'll need to know what is this mapping, what is this, like how many volt for a kilogram, or how many volt for a certain temperature difference. Also, it's not always a linear relationship. Sometimes it's kind of like something that you will see here or something you will see here. So again, that's just kind of, in general, analog sensors. Then there's these things called digital sensors. With digital sensors, what they do is the sensor has an integrated component on them that then translates whatever you're trying to measure into a series of ones and zeros. And oftentimes that output comes as like already in whatever units you're trying to measure. You don't always have to calibrate it, but generally a good idea. But the problem is, because it encodes into these ones and zeros, you then need these communication protocols, or what they call them, communication peripherals, which allow you to encode and decode that sort of information. Now, there is a lot of these different communication protocols out there, and this is pretty much the reason why. Everyone has their own, and they all have their own strengths and weaknesses. But in when it comes to these kind of hobby electronics, there is pretty much three of the big ones. There is UART, SPI, and I2C. Now, whenever you're searching for sensors, they will usually tell you about, they'll be set up to communicate on one of these three. Now, when you look at your pinout for an Arduino or for a Raspberry Pi, I don't know if you can see this, but for example, right here, there is 4 pins devoted to SPI, to the serial peripheral interface. If you look over here on the Raspberry Pi, here is 2 UART pins. So these are essentially telling you which pins can be used to interface with which type of sensor. And yeah, over here you have, I guess this thing is kind of covering it, but you have I2C here in the corner. So yeah, essentially, you don't really need to write a lot of these from scratch. There is libraries on the Arduino that will allow you to communicate. And when you buy the sensor from some kind of a hobby shop, they will usually have tutorials on how to exactly communicate with them. It'll be what to send when you're trying to request information, and then what kind of information you will get back. Okay, so let's look at a few different sensor types. And that's really, there is, I'm going to say hundreds or thousands. So the first thing that you have is essentially switches and buttons. And what they do is they essentially act like an open wire or a closed wire. And when you close the circuit, they allow current to flow, and then you can either measure 0 or 5 volts, depending on how you have them hooked up. So switches and buttons, you can definitely get creative there. You can have bump sensors, so if your robot hits something, you can create them. It doesn't have to be like a physical switch. You can just create something that is spring-loaded, and then it connects, and that's your bump sensor right there. Yeah, and it really depends on how you're going to connect it. If you want to measure distance, there is, again, hundreds of options. It is kind of sorted by the number of dimensions that you would like to measure. In one dimension, there is these kind of sonar sensors and any kind of one-dimensional sensors. If you want to measure things in 2 dimensions, again, the price drastically increases as you go from left to right here. In 2 dimensions, essentially, you have this laser and kind of like a laser rangefinder and a rotating mirror. And then it kind of sweeps an area, and it'll kind of tell you and provide you with a map of kind of what's around your robot. So if you wanted to build something like that, then you can get a 2-dimensional map. These things have a field of view, so you can get a, well, I think you can get a 360, but you have to kind of structure your robot in such a way that it does not interfere with its own laser sweep. And then you also have 3 dimensions. Back in the day, the Xbox Kinect sensor was a very popular sensor to use. Now, autonomous cars have LiDAR, which tells them, gives them a 3-dimensional map of whatever is around them. You might get a 1-dimensional sensor that is analog, but because there is a lot of information coming back from these 2 and 3 dimensions, it's all digital. You're going to have to communicate with them via some kind of a library. You can also use infrared sensors. So infrared sensors, you can use them for a lot of different things. For example, a remote has, that's how it communicates with the TV. It has a little LED that you cannot, that is outside of the visible light spectrum, and then it communicates with the television. But you can also use it to detect things that are nearby. And the way you can kind of get this integrated sensor package, which has an LED emitter and an infrared receiver. And then as things come closer, the amount of light reflected off of that object becomes larger and larger, and you can use that. You can use this kind of potentiometer to adjust the distance, or you can use it as a kind of a proximity sensor. Accelerometers and gyroscopes, you might be familiar with those from the Wiimote. Alternatively, you also find them in pretty much most mobile robots because they can tell you the attitude of your robot, so like the tilt angle, and also the accelerometer will point downwards towards where gravity is pointing. So that's always good to know if your robot is upside down or currently undergoing some kind of a maneuver where it is falling around. You also find them a lot in drones. Every drone has them, and it's kind of uses it within its control system. Again, there's a lot of information coming back from these. Also, every cell phone has one of these in there as well. So if you really wanted to, you could just take your cell phone and put it on there and start recording information on your mobile robot. If you're trying to measure speed and position, then you can use a motor encoder. When you buy a DC motor, you really only need 2 wires to make it spin. There is the positive and a negative. You just put it to a battery to make it spin one way, you reverse polarity, and then it spins the other way. Now, oftentimes you will find these kind of like attached bundles with a whole bunch of wires coming off, and that's because there's a motor encoder on there. With motor encoders, there's 2 different types. There is the relative and absolute. The relative is essentially, it's kind of a light source and a detector, and it has this disc that has these slits in them, and as it spins, this light is interrupted. So the faster it spins, then it can tell, you can measure that. So like the more frequently that light beam is being interrupted. So with relative encoders, there's a few issues. The problem is that if you were to, it can tell you how far something has spun, but it doesn't tell you where it started. So if you were to lose power to your robot and start it up again, now it doesn't know that it is at 47 degrees. Oftentimes, for example, in CNC machines, they have relative encoders, but what they will do is they will go towards home. So you start the machine, and then it will move the motor all the way until it hits a physical stop. And then you know, okay, now I'm back at 0 or back at 90 degrees. Alternatively, you can get an absolute encoder. So an absolute encoder is a similar kind of concept where it has this light detector, but it has this strange kind of pattern on it. With an absolute encoder, the more accurate it is, the more expensive it will be. So with an absolute encoder, let's say you put your motor to 47 degrees, you turn it off, turn it back on again, it will still know that it is at 47 degrees. So that is actually very useful for if you're expecting to lose power, which you probably should be robustifying your machine. I guess, how does it work? If you look at this disk, you have all these kind of strange patterns. So if you look at this inner pattern, right? If you had a simple detector here, you could tell whether you are in this half or in this half, right? Depending on if it's seeing a black or white. And then if you then add another one out here, now you could tell whether you are in this kind of quadrant, if it's measuring white-white. If it's here, it's white-black, or black-black, or black and white. So it kind of like, depending on where you are, it measures a different kind of string of black and white. And again, if you can see here, it's really, really fine. So the more accurate you want your position, the more expensive it'll be. And then sometimes with a DC motor, you will also see something attached at the front, and that's usually a gearbox. That's kind of like a gear reduction. So usually a motor will spin at like, I don't know, 1,000, 2,000 RPM, which might not be something that you would want your specific machine to work at. So you add a gearbox in front. Okay. And then there is camera sensors. This is just a little bit of research I did. I don't know if this will play. No. Okay. Essentially, it was kind of allowing a drone to track a moving target. But camera sensors have come a long way. One of the big issues with them is there's a lot of information coming back from an image. So you also need a lot of computing power. But it actually has come a long way in the last like 10 years. And there's a lot of systems that offer services. AWS from Amazon and all of these big cloud providers, they have services where you can just upload images and then you can label them and say, this is something, and then they will use their cloud architecture to give you a detection. So you can, they usually charge you like a fraction of a cent per image or something like that, but you can create a system where you upload an image and then you let Amazon or Microsoft tell you what it is that you have. But then again, the problem with those things is now you have to create something that uploads an image, which requires some other kind of infrastructure. Plus, you also technically get charged a small amount, but with the systems, I think it's relatively inexpensive, and you might get some kind of a trial account, especially if you're a school. All right. So how do you go about like selecting a sensor? The first thing you should start with is know what you want to measure. And that one could be straightforward, but it's not always. Sometimes you think that's what you want, but then when you actually get it, it might not be. So yeah, just let's say you want to measure distance, like in the activity that's coming up. And then the second step is know what you will be measuring with. That one is important because when you're looking for sensors, remember those communication protocols? Not every different type of microcontroller has access to all of them, so you just got to be aware of that. Also, if you're kind of Googling a specific sensor, some of these will have, they will be targeting specific microcontrollers or single board computers. Now, you also don't always need an Arduino, or you don't always need a single board computer like a Raspberry Pi, and there's hundreds of alternatives these days. One interesting thing about the microcontrollers is if you have a very simple system, it's definitely the way to go because they're more robust and they use a lot less power. So step 3 is to shop for sensors. And this is kind of the difficult way, where you go out, you look for a data sheet, and you see something like this. You have the actual sensor, and then it'll tell you what else to connect. You need 4 capacitors, 1 resistor, and that's just for a single sensor. If you have, let's say, this one is a proximity sensor. So if you have 4 proximity sensor, now you need 16 capacitors and 4 resistors. So it definitely just balloons pretty quickly. So don't do that. Keep in mind the sensor packaging as well. It really depends what you want to do, right? So if you have a surface mount component, they are actually very cheap. I think for about $100, you can get a spool of dozens of them. And they are not really for the hobby kind of maker. They're more for like pick and place machine to mass manufacture circuit boards. I have seen people solder them, but that's, yeah, those things are so small, if you lose them in a carpet, like you'll never find them again. So then there's through-hole components. These ones are made for things like breadboards. And I can see you use them, but honestly, save yourself a lot of trouble and just get these breakout boards. They are a little bit more expensive, so here you're looking at a couple of bucks. Here you're looking at maybe 15 to 20 bucks, but you can, if you look here, they have all of the capacitors and all of the resistors. All you have to do is connect to these pins here, and then that's it. That'll save you so much work and so much hassle. Also, every time one of these companies makes a breakout board, what they do is they will also provide you with a tutorial for a Raspberry Pi, for an Arduino, or similar kind of thing. And they also provide you with the libraries. So try to do that. And then alternatively, you can go the lazy man's route and get one of these kind of USB sensors. You plug it in. It's kind of just like a box. If you are trying to measure one thing, it's pretty simple. You install some software on your laptop. But the issue is you might not be able to get that information off of it very easily. It's kind of for one-offs or for like little test stations that you might have. It's not the greatest. Plus, you'll be paying like like $100 for something like that. But if you're trying to measure something simple, it actually might work quite well. It really depends on what you're trying to do. When you buy something like this, they will tell you, put the wire from here to here. They will tell you everything. You don't need to really go into the weeds of where do I put my resistors, where do I put my capacitors. A few other things to look out for. There is things like accuracy, the range of measurement. Depending on your sensor, if you're trying to measure distance, right? If you're trying to measure, like for a mobile robot, what is the field of view, what's in front of me? Are you looking for 0 to 1 meter, or are you looking for 1 to 10 meters if you're out in the field somewhere? So keep those in mind. But the thing is, the larger your range, the smaller your accuracy generally. And then power consumption is also a big one. If you get rechargeable battery packs, you won't be going to the store and buying a lot of batteries. So try to get one of those as well. The next step is to connect up your sensors. Depending on which route you went, it can be either as easy as the one on the right, or like this thing that I was doing during my master's degree. It can look like something like this. If you, on the other side of this breadboard, it looks a lot worse. There is wires crisscrossing. So try to avoid that. Spend the extra couple bucks and get yourself a breakout board. Also, label your wires, and once you get it working, take a picture of your wiring. That will save you so much hassle, because you'd be surprised how often people will get it working, they get excited, throw it in a backpack, go home, come back, take it out of a backpack, and everything is all over the place, and they don't remember, and they're back where they started when they started. So don't do that.
How are you labeling your wires?
Well, it depends. So black is usually ground, and red is whatever the power, and then anything above is really just preference. You could do certain color for a certain sensor, or here what they do is I think they're using an I2C. They have for a clock a blue versus the other one for a green. So
you're doing a color legend on this side, sort of?
Yeah, it's really, as long any system is better than no system. And then you will be doing an activity later. So this is just kind of a simple connection here from 4 pins and then 4 pins right here. I'll just keep it up for a little bit. This is a ultrasonic sensor, and you just connect it up, and then you're off. And then the last step, after you have everything connected, after you've done the electrical connection, is to write your code. So very likely, you're going to be interacting with these things called GPIO pins. GPIO stands for General Purpose Input-Output. And the Raspberry Pi and the Arduino and all the other microcontrollers, they have those pins on them. And the way these pins work, they have 2 modes. They can either be an output, so they can be set to either give you 0 or 5 volts, so they can send an output, or they can read an input. They can read the voltage of whatever you're connecting to it. Now, it's a bit more complex. There's analog and digital measurements. For example, digital pins can only read 0 or 5 volt or 0 or 3.3 volt, whereas analog input pins can read like whatever, like 3.7 volts or 1.75, things like that. But that's not really important. When you're programming, you're essentially setting them as an output or as an input. So this is the Arduino IDE. Some of you might be familiar with it. Others might not be. But essentially what you do is you write your code, and I believe that it's using some kind of a C language. And then you compile it where it checks for any errors, and then you upload it to the Arduino. Once you upload it to the Arduino, it just runs this code. And the way you structure your code is kind of in 2 sections. There's the setup function. Now, the setup function runs once. So when you kill power to the Arduino and plug it back in, it runs that code once. And then there's the loop function, and then that one is run repeatedly. And this is going to be for your activity later. So you can have kind of a code block up here where you just define a few variables. And then in the setup function, you have the serial.begin. That kind of initiates communication that allows the Arduino, your laptop to read whatever the Arduino is sending back over the serial line. And then you set these 2 pins as an output pin or an input pin. And then within the loop, so the way the distance sensor works, it requires a pulse from your Arduino to get started. And then after a certain amount of time has passed, your computer can then read the echo pin. And then you can go ahead and then you can print out the measurement. But yeah, that's going to be part of your activity later on. And then you generally, because this is a loop function, you generally want some kind of a delay statement. Otherwise, it'll do it as fast as it can. And these microcontrollers are very fast, so you can get it, I don't know, 1,000+ times a second. So you generally want to have some kind of a delay statement that will ensure that it only runs once a second or 2 times a second, so it's very predictable in how it works. And then the last step is calibration. Oftentimes you get a sensor and it'll come pre-calibrated, but you want to be sure that whatever it is, that the sensor is working how you expect it to work. So calibration is essentially looking at what your sensor is measuring and then comparing it to a known value, okay? When you buy a scientific scale, it will come with a very accurately calibrated weight, like 300.000 grams, that you can use to check that your scale is working properly. So this is essentially kind of another act of calibration. For your distance sensor, what you can do is you set up your sensor and then you put an object a known distance away and literally just use a ruler and then plot it on a known distance versus measurement. And then you move your object further away and then you plot it again and then you create a line of best fit, and that will tell you the mapping between what your sensor is measuring and a known, like an actual distance. This is something that you want to do even if they tell you that your sensor is pre-calibrated, because you'd be surprised how often it is actually out. And then once you have this kind of relationship, you can put the object at any distance and it will tell you the rough, like the actual distance. Okay, once you have done all this, chances are something will not work. And there's a couple of ways that you can troubleshoot. And I like to think of it as a divide and conquer approach, right? Putting it all together and then trying to troubleshoot it all at once is really going to be very frustrating. So I like to think of it as wiring and connection issues, coding issues, and then function test, right? Function test is, does it work how it is expected to be? So the first thing is wiring and connection issues, and there's a couple of tools that can help you. You can trace every wire, like manually. You can check that every pin is actually where it's supposed to be. Even myself, because on an Arduino or on a Raspberry Pi, they're all so close together, sometimes you think you connected somewhere, but it's actually not. So just trace it yourself. Alternatively, use a voltmeter and use the continuity test setting on here, which will beep whenever there is a connection between wires. Make sure that if you do that, that whatever thing you're testing is turned off. We actually had a guy at work catch something on fire because it was powered, and he used his voltmeter to test the connections, which ended up causing a short, which ended up causing a fire. But yeah, the whole place was full of fire extinguisher dust. But yeah, likely at the voltages that you're running it, it's not going to cause a fire, but just make sure it's turned off. And then yeah, also color code your wires. So code troubleshooting is actually quite a lot more complex. Again, try to do the divide and conquer approach, kind of test it section by section. What I like to do is I like to go ahead and use print statements all throughout, right? Just make sure that if I assume that a variable is going to have that value, doesn't matter, just print it out. That way you can trace it out. Some of the more advanced programming environments have this thing where you can set breakpoints and step through. I don't think that the Arduino IDE has that, but some others might. And honestly, check for brackets, line endings. You have to have a semicolon at the end of every line. Check for division and multiplication. There is a difference between multiplying or dividing by 6 or 6.0. It's going to give you drastically different values. In some of these languages where it matters. Python, it should be okay, but on something like an Arduino, it will make a difference. That's why I'm saying to make sure the print statement. That way it'll tell you what the value is. And there's also the buddy system where have someone else look at it, because they will generally find your mistake a lot quicker than you can, because sometimes you stare at code for too long and then someone else might find it a lot faster. And then there's function testing. Does it behave as expected? Essentially, you'd be surprised how many times engineers who should know better just assume that something works without just a simple verification. Does a distance sensor measure distance? It seems a very obvious thing, but put something in front, measure it, okay, it works. Then move it to somewhere else. Did that change proportionally? Does a light sensor measure illumination? So essentially, cover it up, see what happens. That is a very simple way of checking if something is working correctly, and you'd be surprised how much headache it will save you. And then finally, if you just can't find anything, you can always ask the community. There's a massive maker community that will tell you, they will have code examples, or they will tell you what to do when you get stuck. And yeah, that's pretty much it. I just kind of have an example of one last thing that you can do. This is an example from work, actually. So what you can do is always try to plot out your information, right? So here we have, there is a pick arm that kind of comes out and grabs something and then pulls it back. And here we have current draw versus position. So on this specific one, the current as the pick arm extends is just like pretty irregular, and then it comes back here, so it looks like it's fine. And then on a different robot, we had the following profile, which means that even though we couldn't see it, we could actually sense that there is something wrong with this specific location, because for whatever reason, the current spikes in that location, and that's pretty repeatable. When we took it all apart, we actually found that there was a bolt protruding, and that's what, as the arm was coming out, it was actually like jumping over the gears. So this is another way. Plotting out your data will really save you a lot of headaches and will give you some kind of an insight that you might, you would have otherwise not gotten. So yeah, and that's pretty much it for me. Thank you very much. Do you guys have any questions? I very much like Python. Python actually, it's the largest growing language at present right now. It's very forgiving with those, you don't have to define things as an integer or as a float. So you can just say variable 1 equal to 7, 7.0. It'll keep that in mind. Also, it has a lot of very good, it's not a compiled language, so you don't need to write your code, compile it, which takes usually some amount of time, and then upload it. You can just kind of run it in step through it. You can run it line by line. So it's really good for that. And plus, I use it at work. So.
What's the applications of Python versus other languages?
So right now, it's kind of big in the data science and machine learning community. So because of that, it actually skews pretty highly on the income chart because of right now, everything is about data and machine learning. So it's actually, if you learn it now, you'll be very well served in the future, especially if you're in high school. You can use it for pretty much anything. A lot of web servers run it. You have libraries for a Raspberry Pi that do all of this GPIO communication. So it's really, I like it quite a lot. It's very forgiving. There's, yeah.